Okay, so we were on finite waves, right? So we said that the for the unsteady 1D flow, the continuity equation and momentum equation. So let's start from there. So what we had was the continuity equation for unsteady right, for unsteady 1D flow. We got this in the last lecture, so we wrote it out to be okay. So let's call this as say 1, okay, and the this is from the continuity, and from the momentum conservation what we got was this. So this is the other the momentum conservation equation. Now what we're going to do here is basically what we tend to do always, which is play around with these equations, right, and see what if we can get any more information from this. Okay, so our main task out here is basically to solve, right, to solve for the pressure, the velocity, etc., right, and in order to do that, we sort of going to play around with these equations. So now let us do this. So we'll do two things over here, okay. So let us take the second equation, okay, and add to it. Okay, so what will we get in this case? Okay, so if we do that, so what we're doing is multiplying this equation, first equation, by a by rho, okay, a by rho, and adding it to the second equation. Okay, so what we get is this. Okay, you can sort of do it yourself once to see whether this is correct or not. Okay, so then what we get is this. Okay, right, this is what we get. Let us call this equation as 3. Okay, so this is what I did. So I multiplied the first equation with a by rho and added that to this, so I end up with this. Okay, so now the next thing is, let us do this. Let us take the second equation and subtract from it this a by rho into the first equation, right? Now if I do that, then I get this. Okay, okay, so this is what we get. Now let us look at this equation over here. Okay, rather this part of the equation over here. So if you see that this is essentially, so del u del t plus u plus a del u del x, right. Now if you remember the concept of the derivative, right, or the total derivative. So this is essentially the instantaneous velocity, the instantaneous acceleration, right, and this is the convective term, right. So this is happening because of the change at each location over time, and this is because of the movement of the particle from one place to the other. Therefore that is the convective term. So therefore this term I can actually write it as du, isn't it? So this is du when of course the velocity with which it is moving, let's call that as Vx, is v plus a. Okay, and it is similar here. So this is the change in the this is the local change in the pressure, and this is the convective change in the pressure. So we can also write this as dP, right? So therefore we can write equation 3 in this form. We can write equation 3 in this form. Right. So if I do that, okay, so if I do that, let me call this as equation, say 5. Now similarly, if you look at this equation here, okay, now let us just note here, in this case Vx is u plus a. Okay, so now if you look at this equation similarly, so again this also we can say this is the local velocity change, and this is due to the convection. Okay, so then this also we can say as du. There is however a difference, and this is dp. The difference however here is that the velocity with which the particle is moving is u minus a, right? So again for that case we can write du minus 1 by rho a dp is equal to 0. Let's call that a 6. In this case Vx is u minus a. Right? So we can write that. So therefore, what does this exactly mean? What does this exactly mean? Okay. Now, if you have a Mach wave, right? If you have a Mach wave, then if the particle is moving in the direction of the Mach wave, then you have this equation, right? And if it is moving in the direction which is opposite to the Mach wave, then you have this. Okay, so that's what this equation essentially means. Okay, now if I now these two equations actually, okay, these two equations 5 and 6. Okay, now these two equations actually they form the basis of a very powerful method in especially compressible flow, which is the method of characteristics. Okay, we'll sort of begin that. So these two equations are the basis of the method of characteristics, and these two relations are called the compatibility relations. Okay, and these 5 and 6, okay, are the compatibility relations. Okay, now we'll see why we call it method of characteristics. Okay, now what we will see over here, that the solution to these equations essentially lie on two lines. Okay, lines. So if the solution to this lies, say u plus a, so essentially if I draw the dx dt plot, okay, if I plot this, okay, now if you kind of recall what we did last time, so this is the solution to this lies on a certain line. Okay, and in that line the particle velocity is what we are trying to plot in that xt diagram. Now in this case we know that the particle is moving in the direction of the Mach wave, right? So dx dt is positive. So therefore if I have, say, this is an arbitrary curve, whether it can be a straight line or a curve, we don't know. So just for conjecture's sake, at this point of time we're going to draw a curve. Okay, so here, so this is my dx dt, right? The dx dt for this curve is u plus a. Okay, this is the line, and for this one, this lies on another line which is moving opposite to the Mach wave. So in that case, we will have something like this, say. Okay, this line, and for this case, we have okay. Now these are the lines which are called as characteristics. Okay, these lines are called characteristics, and these, so therefore this is going to be called a C plus characteristic for a right running wave. Okay, and this one is going to be called C minus. Well, C minus for the characteristic wave. Okay, so essentially, this is the basis of the method of characteristics. Okay, so what we will okay, so now that we've sort of got an idea as to what that is, let us go ahead and do some math, okay, and see how we were going to actually use these characteristics, if at all we're going to use these to solve some practical problems, namely the shock tube expansion wave. Okay, so now if you look at this, okay, what we're going to do in here is integrate these equations 5 and 6, and let's see what we get. Okay, so if I integrate this, okay, if I say integrate equation 5, okay, so what we're going to get is right. Okay, so this is what we're going to get. And let us call this as, okay, so this is what we get from 5, okay, and from 6 what we get is okay, again this is a constant. Okay, now let us call this as J plus. Let us call this as J plus, okay, and let us call this as J minus. Okay, we're going to call it this. Okay, so essentially you can see what we're doing. So this integral, this J plus, is actually constant over the C plus characteristic, isn't it? And the J minus, which we got from integrating equation 6, is the integral which is constant over the C minus characteristics. Okay, now let us go and let us try and integrate this part. Okay, how are we going to do that? Can we integrate this? Now without going into the, I'm not going to do all this detailed integration here, but I usually tend to give out my notes to students if they ask for it. So I have it all sort of done in detail over here. So if you want to look at it, you can ask me for it. I'll scan you and send it, or you can do it yourself. I think it's not too complicated. I'll just give you a brief idea as to what are the relations I use to integrate this. Right? You can do it yourself, but if you can't, then you can take a look at my notes. Okay, so what we will do here is use these relationships. Okay, before I do that, now this J plus and J minus have another name. Okay, they're called basically Riemann invariants. Okay, so these are called okay, so these are basically the Riemann invariants, J plus and J minus. Okay, so now say now for a calorifically perfect gas, we know this is true, and this is isentropic, right? So using the isentropic relationship, which is P2 by P1 and so forth. So what we can write is, so okay, let me write this. So P2 by P1 is rho 2 by rho 1 to the gamma is equal to okay. This is equal to T2 by T1 gamma by gamma minus 1, right? So gamma by gamma minus 1, right? This is what you get. So therefore from here what we can also get is p by t to the power gamma by gamma minus 1 is a constant, and p by rho to the power is equal to constant. Okay. So now if you look here, so A you can represent from A is rho p by gamma. Okay. Then rho you can get dp. Okay, and you can get rho. So then you should be able to integrate this. Now if I do that, okay, if I go ahead using these relations, okay, if I integrate this, what I get is this. Okay, what I get is this. Okay, so basically then what happens is that so then J plus, okay, now J plus becomes right this, and J minus right. So needless to say that this is constant. Okay, so this is a constant. Along C plus, right, and this is a constant along C minus. So what we have essentially been able to do here, okay, just sort of take a step back. Okay, so we got these compatibility relationships. Okay, we got these compatibility relationships combining our governing equations for a finite wave. Okay, now when we do that, then we see that on integrating these two compatibility equations, we get these two Riemann invariants, okay, and we see that this can be further simplified into this. Okay, and what this is telling us that on a right running wave, on a right running characteristic, okay, C plus, so we have J plus. In here we have J plus, okay, and on a left running characteristics we have a J minus, okay, and J minus is nothing but, so and this is constant on a particular C minus. This term, a combination of the velocity and the speed of sound, is constant on a C plus C minus characteristic, and similarly here this is U plus 2a by gamma minus 1. So essentially what we see is that the solution, right, to the compatibility equations lie on certain lines which are known as the characteristics. Okay, and this is the new information that we are getting now. Okay, now we have to see that how we are actually going to use this. Okay, how this is going to be put to use. So therefore now if you look at this, okay, now if I come back and again look at this, I can write here that A, okay, from these two equations is essentially okay, so A is gamma minus 1 by 4 J plus minus J minus. Okay, if you sort of, you can, you know, cross check this. Okay, so and U is J plus plus J minus. Okay, so I am basically using the writing the velocity of sound and the local velocity in terms of the Riemann invariance. Okay. All right, so now let us do this. So now that we have sort of found out a way in which we can you know, evaluate a finite wave, let us go and see how we are going to apply this, for example, to the expansion fan in the shock tube. Okay. All right, so to do that, let us okay, so let us go back here. Okay, so this was our shock tube, right? This was our shock tube. Now we've done the when we break the so shock tube is essentially what? It's basically two chambers in which you can have two different gases or the same gas which are under different conditions. They are separated by a diaphragm which we break by a mechanical means or electrical means at some point of time, and what that does, it sends a shock wave traveling to the right of it, which is moving into quiescent flow, and we were able to calculate the properties of the fluid once the shock wave moves, okay, behind and in front of it, and that we have done. What was left to do is, when we break the diaphragm, there is an expansion wave which travels to the left of it, which travels basically in the direction opposite to the shock wave, and what we are left to do is find out the properties in front and behind of this expansion wave. Okay, so this is what we have. So if you, this was the contact surface which is moving again to the right, and we had an expansion fan, right, say something like that, and that was moving into this region. Okay, so this region was say 4 and this region is 3. Okay, so this is it, and this is okay, I'm sort of breaking that region out. So therefore in here, this is say at time, this is at a non-zero time, okay, at some instant of time when we break it, then this is what happens, okay. And what essentially happens is that you have the shock wave which moves to the right, and that induces motion in the fluid which is behind it, okay. So we will have a velocity in this as well. Let us call that as u3. Now this is a contact surface, okay, which moves you know, to the right, basically following the shock wave. Okay, so now that we have this, let us draw an XT diagram for this. Okay, let us draw an XT diagram for this. Okay, now what you can see over here is that this expansion valve, right, all of it originates from one point and then it proceeds, isn't it? Because at the time when there was the diaphragm was present, there was no expansion fan, and then as we break the diaphragm, right, then all these waves, they basically originate at one particular point and then they move forward from it. So therefore at the time 0, at time t is equal to 0, the wave is essentially not there. So just about at time t is equal to 0, the wave is situated here. All the waves are essentially situated over here. Okay, and then they move from x is equal to 0. So that's what this origin here means. This is essentially the location at where the waves originate. Okay. All right. Now, if I do that, so let us call this. Okay. So this we can call, say, as the head. Okay. Let's call this as the head, and this is the tail of the. This is the head and tail of the expansion fan. Okay, so in an XT diagram, what are we going to do here? Basically the velocity, isn't it? So XT diagram, so here, say this is, or say let us do this. So say this is the head. Okay, this is the head of it. And this is the tail of it. Okay, so if you look here, so say this is the tail, okay, and this is the head. Okay, so this is the head, and that is the tail, and then in between of course we have several waves, so on and so forth. So what we see over here, if you look at this picture, so essentially we have several waves moving into the region 4 here. Okay, now U4 of course is quiescent, isn't it? U4 of course is quiescent. So therefore now we have several waves moving into this. Okay, now at t is equal to 0, all the waves originate from here and then they move, right? And in this case we are taking this, you can see I am taking x to in the negative direction. Okay, so that is the reference frame here. Okay, it is moving to my left. Okay, and so they originate from here and then they move into this region 4. So therefore this is the expansion fan, and this corresponds to this over here. So to the left of it is moving into region 4. So this is actually my region 4. Okay, and this is my region 3. Isn't that right? So this is it. Okay, so therefore in here of course, now let us write down. So in U3 region, which is corresponding to this on the xt diagram, okay, we have essentially velocity is U3 and the speed of sound is, say, is A3, right? Now in here what is U, so we have velocity U4, this is quiescent, so this is 0, and A4 is yeah, so that is the velocity of speed of sound. Okay, so this is essentially my region. So therefore if you remember, okay, now if you what we did just now, right, what we did just now here, if you look at this, okay, this is the xt diagram, right? So we said on a left running characteristic. So now on a left xt diagram, on a left running characteristic, okay, we have the slope is dx by dt is u minus a, isn't it? Which is that the particle is moving away from the wave, okay, and it is moving with the velocity basically u minus a, right? So dx by dt. So now these say are the characteristics. Okay, so if you consider these are C minus characteristics, right, because the particle for a left running wave, right. So let us say these are, say, C minus characteristics. These are all C minus characteristics on which this is the slope, isn't it? So the slope is u minus a. So this is u minus a, so this is essentially dx by dt. This is the slope of this characteristic, right? So if I look at that, then in that case, what is the slope of the head of the expansion wave? Okay, what is the slope of that? Because u4 is 0, right? Similarly, what is the slope out here? So this is, isn't that right? Okay, so that's what we have from here. Now what should be asking at this point? So I say that for this is my expansion fan and I am drawing the characteristics, okay, because why am I doing this? What am I doing this here? Okay, basically what I need is the properties, okay, across the expansion fan, right? And how am I going to do that? Well, I say that these are my governing equations, right? These are my governing equations of an expansion fan, and what I have found out that the governing equation, the solution to that, especially solution to that, lie on lines which are known as characteristics, and these characteristics for a left running characteristic. So I am basically plotting that on x by t I am doing an xt plot for that, and on these lines which are essentially the C minus characteristics. So, these are the slopes. Okay, these are the slopes. So, in this case what is these are left running because the particle is moving in the direction opposite to the actual wave. Okay. Now, if this is it, so then okay. Now, the question to ask is, what is the difference between this plot and this plot? Okay. When I did this and I said the solution to the governing equations or to the compatibility equations basically lie on lines, okay, and we are not specifying whether this has to be a curve or it has to be a straight line. These are just lines. Okay. So, therefore, we drew these arbitrary curves. Here, however, I have drawn straight lines. Okay, I have drawn straight lines and I am calling them as C minus characteristics. Okay. So, I think first thing we need to do is prove, let us prove that it is indeed a straight line. Okay. It is indeed a straight line. So, in order to do that, say I will draw for in this case, okay, I will draw two the C plus characteristics. Okay. If I have to draw C plus characteristics, so say okay, is there anything else here? Okay, that is it. Okay. Now, let us do this. Okay, let us draw two, say, C plus characteristics. So, these are C plus characteristics. Okay. So, I have that, and let me draw one more. These are also C plus characteristics. Now, we are going to call these, we are going to call these locations something. Let us call this as A, B. Okay. So, then here on the head on this characteristics, this is C and this is D. Okay. And anywhere in the middle, say this here, anywhere in the middle, this is E and this is F. Okay. So, what essentially we are saying is that we are drawing these C plus characteristics. Okay. So, what we are going to try and prove is that these lines are indeed, these characteristics are indeed straight. Straight for this particular kind of a expansion fan. Okay. So, what I have done here is drawn the C plus characteristics, and what I am doing here is essentially these are intersecting the C minus characteristics. So, therefore, I am calling these, I am specifically locating those points and calling these as, giving them some names. Okay. Now, let us see. Now, in this case, so what we know is that, yeah, these are things that we know, right. Now, so if I go to say in region 4, okay, if I go to in region 4, so let us say, how will we calculate, say, now J plus is constant on a C plus characteristic, isn't it? So, these are C plus which are associated with J plus, okay, and this is J plus, and J minus is on corresponding to, so C minus characteristics, and J minus is constant on C minus characteristics. Okay. Now, let us calculate J plus, okay, for A. So, this A point is in the region 4, isn't it? So, in here this is, okay, this is essentially what? So, now this is the J plus, okay, in the A region. So, this becomes isn't it, and this U4 is 0. So, what we end up getting here okay, is that fine? Now, let us calculate j plus of b. Okay, if I calculate j plus of b, what I get again is u plus 2a by gamma minus 1. Again this is a and this is a, this goes to 0, right. So, this is again 2a for gamma minus 1. So, you can clearly see that j plus a is equal to j plus b. Okay. Now, let's just stop here for a moment and think about this. This may not be true for every possible case. Okay. What we are doing is we are taking the characteristics and looking at it for this particular case. Now, what you see is that this is a region, right. Now, this wave is moving into this quiescent flow, this u4 out here, okay, and they are all originating at the same point. Okay. Now, think about this. Okay. Now, if this did not originate at the same point, if I had another characteristic, this head or this head that I have drawn over here, if this did not originate at this point t, then a and b would most probably be different. Okay. So, this is, so when I say j plus a is equal to j plus b, this is not for every possible application. It is just for this particular case. So, we are applying this concept or methodology only for this particular case. Okay, just wanted to emphasize that. So, therefore, this is my U4 region. Okay, I independently drew two C plus characteristics, and I am basically for t x is equal to on this x line, okay, where t is equal to 0, I am trying to calculate j plus and j plus a and b, and when I do that, the a and b are both in this region, in this quiescent region where u4 is 0, and what I see is that j plus a is equal to j plus b. Okay, so j plus a is equal to j plus b, right. Now let us look at this C plus characteristic. So, the green C plus characteristics, and we know that j plus is a constant over a C plus characteristic. So, based on that, what we can write here is that j plus a, right. Now, this is constant. So, j plus a along the same line. So, C lies, this point C lies on this green characteristic. So, therefore, this is also equal to G plus C. This is also equal to J plus E. Isn't that true? So, essentially what you are saying is on each C plus characteristic has the same, is associated with the same, with a particular value of J plus. In this particular case, I have found out J plus at this point A, which lies on C plus characteristics, right. Now, so therefore, J plus A is equal to J plus C, which is equal to J plus E, which is equal to this value, which we have found out. Okay. So, similarly, when I look at this purple C plus characteristic, okay, what I get, okay, let me write that. So, what I get is J plus B is J plus D F. So, what I am doing is just going at different points of this C plus, okay, and I have on all these points B, D and F, they all lie on the same C plus characteristic, and hence they all have the same J plus, which incidentally we were able to calculate, which is equal to J plus of B, and which is equal to this, isn't it? Now, again, since we know that these two are actually equal to each other, isn't it? If that is true, then what we get is, if that is true, therefore these two are also equal, isn't it? So if A is equal to B, okay, so therefore from here we can also write that J plus C is equal to J plus D and J plus E is equal to J plus F. Isn't that true? So now these two are equal to each other. Okay, then we move out here. Now the reason we kind of are interested by when we say J plus C is equal to J plus D, because we see that these 2 points also lie on a C minus characteristic. Okay, they also lie on a C minus characteristic, and therefore that is important. So therefore what we are saying is these 2 points, these 2 locations C and D, they also lie on a C minus characteristic. They lie on the same C minus characteristics, but they lie on 2 different C plus characteristics, right? And what we are able to see here is that for this particular case, J plus of C is equal to J plus of D, right? And similarly, J plus of E is equal to J plus of F. Okay, so now let us look at E and okay, then let us look at E and F, because that is like for any particular characteristic within the wave. Okay, if I look at E and A, okay, now what we'll do is, in this particular case, if you look at those 2 points, now as we did, we shall be able to calculate the velocity of sound and the local speed using J plus and J minus, isn't it? So now if I look at, say, the point E, if I look at the point E, which is lying on this C minus characteristic, okay, so then say at the point E, okay, so I can write the velocity, isn't it? So now at the point E, I know J plus E and I know J minus E, isn't it? So therefore I can write this okay, and UE is half of J plus E plus J minus E, which we have sort of written earlier. Yeah, I think this should be a minus. Yes, this is a minus. Okay, so okay, I got that wrong here. Okay, and at the point F, okay, similarly, so what we have is AF, okay, is gamma minus 1 by 4, again J plus of F minus J minus of F, okay, and UF is half J plus of F plus J minus of okay. So now what is the slope? Okay, what is the slope of the characteristic at the point E? So what is the slope here? What is the slope here at the point E on C minus characteristics? It is this, right? U minus A. So I can write here the slope here is UE minus AE, right? If I do this, basically I have UE minus AE, and similarly here, you see what I am doing? So then slope is UF minus AF. Okay, so what I have done essentially is taken 2 points. I have taken 2 arbitrary points on this C minus characteristics, right? C minus characteristic which lies anywhere in between this, which represent any part of the expansion fan, and what I am doing here is calculating the slope here and calculating the slope here. Okay. So, using the information that we can get from the characteristics. So, when I write this here, so slope is UE minus AE here, okay, and slope here is UF minus AF. Okay. Now, what we have seen so far, okay, if we go back, is that J plus E, is equal to J plus F. Okay. So, in here, so let us say in here, okay. So, this J plus E is equal to J plus F. Okay. So, why do not we write this as, say, let us just write this as, say, J plus. Okay. So, we will just write this as J plus. Again, we will write this as J plus, we will write this as J plus. Okay. Now, this E and F, they lie on the same C minus characteristics. So, this will have the same J minus, isn't it? So, therefore, this we can write as, say, J minus, this is also J minus, this is J minus, and this is J minus. Okay. So, therefore, what happens to UE minus AE if you look at this? Okay. So, this is essentially, so I am going to just write it like this, function of J plus and J minus. Similarly, here this is also a function of essentially these are same. Now, so therefore, the slope at 2 points, so at the slope at 2 arbitrary points, right, of this C minus characteristic is same, and therefore, we can say that this is actually a straight line. Okay. Now, I could take this E and F or more points, or I can take more than just 2 points, because these are arbitrary points. So, what we were able to prove is that the slope here is the same as the slope here. Okay. And therefore, for example, if I go back here, say, okay. Now, for example, look at this point. Okay. Let us say I have a point over here. Okay. In that case, the slope here will be something like this, isn't it? And say I go to a point here. In this case, the slope will be something like this, and you can clearly see that the slopes are not same, right. However, if you look here, the slopes are same, which is what we get, hence this is a straight line. Okay. So, this is a reason. So, therefore, the C minus characteristics, therefore, or characteristics usually, they become straight lines, okay, when the wave here is moving into a quiescent flow. Okay. And therefore, this is usually called a simple wave. Okay. All right. So, simple wave, and also it is also called a centered wave, because it is a simple wave, okay, because it is moving into quiescent flow, as a result of which all the characteristics are straight lines, and also it is a centered wave because the waves are generating at a single point and then they move away from there. Okay. All right. So, now that we figured that out, okay, so we have been sort of we are in the process of trying to figure out the properties, you know, across an expansion fan in the shock tube. So, what we have, you know, we still haven't done is the actual relation between the properties, which we will do right after this. Okay. Now that we have proved that we basically have a simple wave which is centered at t is equal to 0. Okay. So, and these characteristics are straight lines. So, we will continue with this and get a relation between the properties of the waves, and then we will see how the properties vary, okay, when such a wave starts traveling in the shock tube. Okay, thank you.